All right, let's see what kind of trouble we can get ourselves into here. Let's look at an example. Let's say that I've got some sort of structure here. Some sort of trapezoid. We'll put a circle in it in here. I'm going to shade this area in here. So let's say we're looking at, I don't know, either the end or maybe a cross section of some structure here. Let's say that this width, this total width here is 10 foot on the bottom, and let's say that it's 13 foot on the top. Let's say that it's 3 foot tall. And let's say that I'm just going to point to this guy and say the diameter of that guy is 2 foot. And I do need to know kind of where that circle is located. So let's say to the edge of that circle, we'll say that's 2 foot, and then maybe up to the bottom of that circle is 0.5 foot. Okay, so that tells us where the edge of that circle is located. And the problem's probably going to ask something like, find the centroid of the shaded area. Now, why might we want to do something like this? Well, let's say that, I don't know, this is some beam that we're looking at maybe the end of it, and this actually kind of, we'll say it goes into the page, so to speak, and into what we might call the z-axis. So we're just looking at the end of it, and we want to know where would we apply the weight for this thing? And that's going to be applied at the centroid, which we've already discussed. If the density is constant, that's going to be the center of mass and the center of gravity for the shape. So that's a common thing we might want to know. Now, there's no equations here that we can apply to these curves and integrate between two lines or curves. So we're actually going to have to treat this as a composite body. We can break it up into known shapes that we can find the areas and the centers for, and we'll treat it like a composite body and do it mathematically accordingly. Now, if you didn't know, if you look at the back inside cover of your textbook, most textbooks have got different shapes, and I can't do this very well without changing the angle of my camera. Sorry, it's going to be, go look at the inside cover of your book, but if you've got a circular area, it will tell you the area is pi r squared, and then in chapter 10 we're going to need to know these moments of inertia, and if you've got a rectangle, that's also on here, and there's a triangle and some other shapes in there, right? So there's some common shapes that it will tell you the areas and locations of the centroids of these things. Now, basically the shapes that I'm going to test you on will be a circle, a triangle, and a rectangle. If you can process those shapes and mathematically and know their areas and the location of their centers, you should be just fine. Right? So what would we do with this guy? I would suggest breaking this up. Basically, you've got a rectangular area here, you've got a triangular area there, and then you've got a circular hole right there. So I would treat it as 1, 2, 3 different shapes. Right? You wouldn't necessarily have to draw these out. And by the way, these problems, the chapter 9 and the chapter 10 problems, kind of deviate from the standard draw a free body diagram, sum the forces, sum the moments. How many equations do you have? Do you have as many equations as you have unknowns? No, these centroid problems kind of take two flavors. Either it's going to be something I can integrate between a certain area, over a certain area, or it's something like this where I can break it into some known shapes and use those to find the centroids, or find the total centroid, the composite centroid. So if I break this up into 3 shapes, as I was discussing, I'm going to first break it up into this rectangular area. And this rectangular area, we'll call it 1. and its center is just right there in the middle of it. It's uniform shape. Center is going to be right there at 5 feet. Total span is 10 feet. And by the way, it's going to say find the centroid of the shaded area, and it's going to tell you where do you measure it from, right? It's like, all right, well, how do I describe that? Well, measured from some point, and we'll say some point O, and that'll be designated on the diagram somewhere. Often O is going to be the bottom left-hand corner, kind of like the origin. Mm-hmm. So point O is going to be down here, so I'm measuring the X location of the centroid for this rectangle relative to point O. And I would need to know the same thing for the Y direction, so that would be 1.5 feet up would be the middle of this 3 foot tall rectangle, or 1.5 feet down to get to that centroid. All right, so that would give me, with these dimensions, I could find the area 10 by 3, and I could find the centroid here at 3 by 1.5. Now, my second shape is going to be this triangle. So the second shape is going to be this triangular area. I'm going to draw it out here. Its centroid is going to be right up here in the thickest part. And this triangle, if you look here, so it's 10 foot, we've already said from here. Oh, you can't see that, I apologize. It's 10 foot from here to here. Right, 10 foot from here to here. So it's going to be 3 foot from here to here because it's 13 foot total. So it's 3 foot from here to here, 3 foot from here to here. So it's a 3 by 3 triangle. Right? Now, the center of this thing is, again, right up here in kind of the thickest part. So along the x-axis, it's going to be the centroid of a triangle. It's going to be 2/3 of the length from the thin edge, if you will, kind of the thinnest part of the triangle. It's going to be 1/3 of the length from the thickest edge. Now, this whole span is 3 feet, so that means this little span here is 1 foot, and the other span is 2 foot. Now, vertically, again, it's right up here. So from this edge, this top edge, sorry, you can't see it, from this top edge, it's going to be 1/3 of the length, the total length, from the thin part, or 2/3 of the length. I guess from that, it's 1/3 of the length from the thicker part, 2/3 from the thinner part. So it's going to be, again, it's going to be right up in here, above half. So it's the longer distance here is going to be 2/3. Well, it's 2/3 of 3 foot is going to be 2 foot from the bottom, or 1 foot from the top. That's going to be the center of shape 2. Center of shape 2. Now, again, keep in mind, we're not measuring relative to this triangle. We're measuring relative to some point O down here. So that's going to be 10 foot from point O, the edge of this rectangle, to this is where the edge of of this triangle starts. So it's going to be 10 foot from point O to the plus the other 1 foot to get to the centroid. And then going up, it's just the 2 foot up from the bottom. Now, we're going to see why that's important in just a second. And I've got a third shape, we said. I've got this circle. Now, what I like to do when I draw a hole is I like to put a negative sign next to the number. Right? Its centroid's right there in the center of this circle. So I'll call this -3. And put a point there on its centroid. I need to measure the location of that centroid relative to point O. And I need to describe the size of this thing, right? So again, the diameter of this thing, is, we've said, was 2 foot, or its radius is 1 foot. And what I would always say is we'll leave the measuring the radius to the mathematicians. Engineers work with diameters because you can't measure radius. You can measure diameter and then divide it by half, and that gives you the radius. If you don't believe me, go try to find the radius of a pipe. You can kind of eyeball it, but you can actually measure the diameter. So we tend to think in diameters, and that's okay. This circle, again, is 2 foot from this edge in the x direction, 2 foot from this edge to the edge of the circle. It's a 2 foot diameter circle, so the center is going to be half of that 2 foot, so another 1 foot. So the total distance from point O along the x direction here is going to be the 2 foot to the edge of the circle, then 1 more foot to get to the middle of the circle. It's going to be a total of 3 foot horizontally from point O. And then vertically, they've said it's half foot to the bottom of the circle from point O, and then it's 1 more foot up to the center, so that's 1.5 foot vertically up to the center of that circle. Steve, what the heck are you doing? Well, remember, we talked last time about finding, for any shape, you're going to sum the x location of each individual shape times its area divided by the sum of all the areas. That gives you the x bar. And the same thing for the y bar. So what do I need? I need the y and x location for every individual area, and I'm also going to need to compute every individual area. So I need to know the size and location of each one of those shapes. Now, again, I'm doing a couple of steps here that aren't necessarily required. It's not necessarily required that you do this. If you can ascertain all this information here just based on the one diagram, that's fine. Kind of like drawing a free body diagram. It's a really good idea to do these, but it's not. I won't necessarily count off you don't do it. And another thing that's a really good idea, again, I won't necessarily count off, is if you it's sometimes easier to build a table to organize your information. Right? So again, we're gonna look at each individual shape. So I'm gonna put top row on this table. So I've got 3 individual shapes. So I've got shape number 1, that's my rectangle. I've got shape number 2, that's this triangle. And I've got shape number 3, that's this circular hole over there. And then I'm going to have a total column. Okay. So for each one of these, I need to find its x location, the location of its x center. All right. You don't have to use my exact format of a table, but a lot of people do tend to find it helpful. So if you find it helpful, please feel free to use it. The first shape has an x location from origin, from point O, of 5 feet. And you can go across the table here and fill these all in. But I'm just going to go down the column. Let's do the rectangle first because it's easy. So we need to find its x location, its y location, the y locations of its center. We need to find its area. And then you could go ahead and find the area times its x location and the area times its y location for each of those shapes. So again, we'll do the rectangle because it's easy. So from point O, we said the x location is 5 foot. The y location is going to come next. So from the bottom up, from point O up to the middle of this is 1.5 foot. The area, it's 10 foot by 3 foot. It's a rectangle. It's 10 foot by 3 foot. So the area is 30 foot squared. And so then I'm just going to find this 30 times 5. 30 times 5 is 150. I've got feet squared times feet. That is feet cubed. I've got the area times this y location. So that's 30 times 1.5. Well, if my math's good, and it's normally okay, that's going to be 45 cubic feet. Feel free to double check that. I didn't just kind of do that in my head. And then we can do the other shapes. So I've got this other triangular. It represents this area out here. So I've got this other triangle. Its centroid is up here. It's 10 foot to get out to the triangle from point O. Right? 10 foot to get out here. it's 1 foot in to find that centroid. So a total of 11 feet for that shape too. And then from the bottom, we're going to go up 2 feet from the bottom to find that centroid. So this is just 2 feet. The area, I've got a 3 by 3 triangle, so 1/2 of 3 by 3, that's 1/2 of 9, that is 4.5 feet squared. All right, let's see if I can do these in my head. Might be dangerous. This is 44 plus half of 11, 5.5. 44 plus 5.5 is 49.5. I hope that's right. I hate doing things in my head sometimes, but I'm pretty comfortable with that. Yeah, I'm double checking. I think that's okay. I'll double check these. I'll pause the video here in a second. Just double check these numbers. All right, so for the next row, then I'm going to take this area times the y. So 2 times this area. 2 times the area, that's just going to be 9. 9 feet squared times feet, so that's cubic feet. And then the last one, you can convert this to a decimal. I'm just going to leave it as pi for right now, or at least the area I'm going to leave as pi. Now, the location from point O to the center of this circle, we said is the x location is 3 feet. The y location, again, remember if we go back to the original, it's 1/2 foot up to the edge. It's a 2 foot diameter, so it's 1.5 feet in the y direction up to the center of that circle. And the circle is 2 foot in diameter. Area of a circle, of course, pi r squared, which you can find in the back cover of your book. Again, engineers normally like diameters. So pi d squared over 4, pi d squared over 4, because its diameter is 1/2 of radius. Radius is 1/2 of diameter. So if I have d over 2 squared, that ends up d squared over 4. Okay, so let's see, this is a 2 foot diameter, or we could also say, well, it's r is 1 foot, so 1 foot squared times pi is just, the area is going to be pi feet squared. But it has a negative sign, so negative pi feet squared is going to be that area, because again, it's a hole, it's missing. That's not part of the shaded area. It's been removed, so it's a negative area. All right, these are pretty simple if I just leave it in terms of pi. This is minus 3 pi feet cubed, and this is minus pi times 1.5, so minus 1.5 pi feet cubed are those. Okay. Now the totals, you don't have to total these first 2 rows, but you do want to total the area. So the area is going to be 34.5 minus pi feet squared. This one is going to be, I'm going to add these up, so it's 199.5 minus 3 pi feet cubed, and then this one is 45 plus 9, that's 54 minus 1.5 pi, and those are both feet cubed. Steve, why in the world would you do that? Well, again, remember, composite body, the x bar is going to be the sum of all these x times a's divided by the sum of all the a's. What do I got right here? I have the sum. This is the sum of a. This is the sum of x times a. And this is the sum of y times a. Y tilde a, x tilde a. So those are the quantities I've got there, and those are ready to plug right into those 2 equations. Okay. So x bar is going to be this 199, assuming I've done these right, 199.5 to minus 3 pi quantity divided by 34.5 minus pi. quantity. The top is feet cubed, the bottom is feet squared. Notice the units are going to work out to be feet. And you can run that through your calculator. I'm going to pause here, double check my numbers, and get us an answer. Feel free to pause here, find this one, and feel free to also find y bar over here. Feel free to find both of those. Go ahead and pause. Okay, this is what I got. I get x a little over 6 foot, y just a little over 1.5 foot. It's always a good idea to go back and look at your shape and see if that makes sense. 6 foot would be, so if this is 10 foot across here, it's 6 foot would be a little more than half. So let's say half is right in here. That's going to put you right up here. I'm sorry, you can't see that. 10 foot across here. I'm 6 foot out. It's a little more than half. Half being probably right in here. All right, so I'm a little more than half. So probably right in here somewhere in the x direction. In the y direction, we said 1.59, almost 1.6, so just a little more than halfway up. So probably right about there is probably where we're going to put our G. It's always good to just go look at it and see, does that make sense? Well, it kind of does, right? I've removed some area over here, and I've added a little bit of additional area over there. And so basically, the center of this rectangle is right about here. And so this triangle has basically kind of moved it, and the loss of this and the addition of that has kind of moved it over a little bit and moved it up a little closer to the center of this triangle. It's still closer to the center in the y direction of the overall rectangle, as it should be, because it's the largest shape. But this triangle does pull it up a little bit and over to the right a little bit. And again, this being missing pushes it over to the right a little bit also. So that makes sense. That's kind of how mathematically that should work, or at least theoretically that's how it should work, and you can see mathematically how it should work. So here's your answer. X bar, Y bar. All right, we'll go to the next one.